Hi, everyone. Welcome to the seminar. Our speaker today is Yahav Bechavod. Yahav is currently a postdoc at the University of Pennsylvania, working with Iron Rod. Before joining Penn, he was a PhD student in the School of Computer Science and Engineering at the Hebrew University of Jerusalem and an Apple Scholar in the AI/ML team. Yahav's research interests are primarily in algorithms, machine learning, and game theory, and specifically in the areas of fairness in machine learning, online learning, and learning with strategic behavior. And today he's going to tell us about individual fairness in online classification. Take it away, Yahav.
All right, thank you, Saeed, and thanks for this kind introduction. All right, so today's talk is going to be based off this line of research with wonderful colleagues, with Chris, Stephen, and Aaron Roth. And really, I want to spend the first couple of minutes of this talk in re-examining the commonly made assumptions in the algorithmic fairness literature, as I think they will really lead us nicely to the main motivations of this work. So in particular, I would like to focus on three different things, like first of all, the level in which fairness is defined, the data generation process, and the feedback model. And it will help to look at this running example throughout the talk, and the example would be a loan setting where incoming individuals apply for loans, and a bank deploys a loan policy, and according to the individual's features, then individuals are approved or denied of a loan. Okay. So the first point I want to focus on really is that the bulk of the research is a generalization, but the bulk of the research, like most, really focus on algorithmic fairness definitions that bind on the statistical level. And what I mean by that is, usually the recipe is like you first select a statistic of your choice, then you define a set of groups in the population, and then approximately equalize the statistic across groups. And the focus is really that these group fairness definitions are very weak guarantees for individuals. And this is a toy example from the Cal paper, really delivering this point very nicely. And you can see that if you look at the percentage of accepted individuals, and you look at blue versus green individuals or male versus female individuals, then the ratio is maintained. But if you look at combinations of these features, you can see that for green males or for blue females, they never get accepted, and this breaks as you look at the final level. The second focus that I'm going to look at now is that the standard statistical assumptions may not necessarily hold. So again, this is a generalization, but the majority of the work in algorithmic fairness really operates under these IID data generation assumptions. And I'm going to argue that in various settings where fairness is a major concern, this assumption does not necessarily hold. And this is due to, for example, strategic effects where you have individuals modifying their features based on knowledge or in anticipation of the deployed policy to get a better prediction, or whether choosing whether to apply or not based on their perceived chances. So you can see all of the online websites which offer advice for individuals on how to boost your credit score fast, and some of the advice is like obtain additional credit limits, or reduce your debt. But the point being is that in anticipation or seeing this policy is actually changing the way that individuals are acting and changing their features. And you could think, well, this is only a concern where the deployed policy is known to people, but this is a nice example from SCHUFA. This is like the German FICO Germany's largest leading credit bureau. And you know, the recipe is like obviously not known to individuals. And this OpenSCHUFA is like a recent crowdsourced project where try to look at specific problems in the algorithm, but they don't know the algorithm. So they really wanted people to report points or like their perceived scores, and they collected 4,000 of these scores, and they tried to sort of like reverse engineer the algorithm. This is not for strategic manipulation, but I'm saying this might also be a concern where the prediction rule is not accessible to individuals. And two other effects that I'm going to that I'm looking at is the distribution that shifts over time. You know, for example, the ability to repay a loan may be affected by changes to the economy or recent events, and the adaptivity to previous decisions. And the third point is that while most of the literature really looks at full information settings, either in batch or online settings, and some papers also look at the bandit setting. However, so if you look at admissions or loan approvals and many other domains where fairness is a major concern, feedback seems to follow a different structure. And the structure is this one-sided, only positively predicted label information only, which means that we get the label information only for accepted individuals. And in particular, having this structure also means that in batch settings, we have to be very careful because the data is always dependent on formerly deployed policies. And if these policies were, you know, for example, discriminatory or inaccurate, there's a chance that we are going to inherit some of these biases of historical policies. And just in particular, note that this is not a bandit setting. So if we look at the one-sided setting, for a bandit setting, we have you know, the information for the action that we choose. But here, if we deny a candidate of a loan, we see no feedback for any of the actions, not the action and not the counterfactual. So this is a different setting. All right. Questions so far, or is everything good? All right. Cool. So after this first part of the talk, so the main focus is going to be this line of research in which we try to, you know, sort of like remedy these three focuses or like give solutions by offering meaningful guarantees to individuals and by extending beyond statistical assumptions and possibly with one-sided feedback. So the first part, we'll present the fairness framework, which is this metric-free individual fairness with the assistance of human auditors. And then we will see the individual fairness with online learning setting. And later we will see how we can connect this setting to the literature in contextual combinatorial semi-bandits and establish criteria that go simultaneously, that hold simultaneously for accuracy and for fairness. And if we have time, we will go over the construction for Oracle efficient algorithm. All right, so again, we look at this problem where fairness breaks at the individual level. And what we are going to focus on in this talk is the notion of individual fairness, which was introduced by the seminal work of Dwork et al., Fairness Through Awareness. And the assertion is, you know, on a high level that similar individuals should be treated similarly. And the way that they formalize it in the paper is like a Lipschitz-like condition, where you have a randomized predictor, here denoted by H, and the difference in predictions has to be no larger than the distance according to some metric between individuals. So this D is measuring really how similar are two individuals in the context of a specific task at hand. All right, so the main challenge with operating this framework of individual fairness is that in many settings, this metric is unavailable. So it's also unclear how can it be elicited or learned. And so, you know, if you ask people, they might have different opinions of who is similarly situated in the context of this task, or, you know, if your individual has an idea of what should be similar, maybe enunciating the metric exactly is not really easy to do. So in the context of credit, you could ask, you know, what is the exact formula for similarity for loan applicants? And, you know, even a trained expert could say, well, it's hard for me to tell. And you can also, you know, maybe have like an easier question, and what is the exact distance between individuals? And but still for human auditors, that might be a challenging task. So in this line of work, we really follow this notion of fairness violations. So namely, we ask the auditor to spot violations of individual fairness, which means, you know, to report a pair of similar individuals where things were treated very differently by the algorithm. And this is, you know, follow this idea of the auditor knows to detect unfairness when he sees it. So, and this is some really nice prior work on individuals, and, you know, starting with the Dwork et al. Paper, we'll introduce the notion. And Guy and Gall's paper will assume that the metric is given. And Christina Elvento's paper in 2020 is trying to actually learn the metric via distance and numerical queries, which we will try to not do, and also try to this easier type of questions to auditors. And we really follow the Gillen et al. Paper that is the last one here, which sort of like introduced this auditor model which knows unfairness when he sees it. And so we are going to follow this fairness framework, but we're going to generalize it not to hold specific parametric assumptions, and also to have multiple auditors, but we will see in the next part of the talk. So some definitions that we are going to need is X is the instance space, Y is a label space assumed to be binary, H is a class of predictors, and we assume it has a constant predictor, and we allow for convex combinations of hypotheses to be deployed, not just single ones. The misclassification loss is simply the 0-1 loss. And we have the extended version for 0-1 loss for a convex combination, which means the expectation. All right. So good. So individual fairness. So how do we approach this? So we assume that there is a distance function. So for a single auditor, we assume that the auditor holds a distance function, which captures the similarity or the distance between the individuals in the space. And we define an alpha fairness violation as a situation in which, for a given policy, pi here, that the difference in predictions is larger than the distance between the individuals according to the implicit belief of this auditor, plus some alpha slack term. And okay, so in our line of work, we only require the auditor to report one alpha violation if one or more exists. So the definition of this primitive means of the auditor here is given a set of k individuals, if there is a policy that is predicting, let's say, creditworthiness, if there exists a pair on which the auditor thinks there exists a violation, the auditor has to return this pair. So if multiple ones exist, he only needs to report one. Okay. So if no violation exists, it reports that it sees no unfair treatments. And well, you could ask, so like the auditor's preferences or human preferences in general that may be inconsistent, or what happens if the specified, the feedback from the auditor does not follow metric form. So like, for example, the triangle inequality could not hold. And so in this line of research, we drop these assumptions on the metric and the parametric form, and we allow, we just require that the similarity function is non-negative and symmetric. And far we've focused on having a single static auditor, but we are going to generalize this in this work to multiple auditors. And so like if you think about it, so it's highly unlikely that stakeholders would entrust a single auditor with fairness related judgments. So this is due to like human implicit biases based on many factors, due to the fact that having the same auditor over a long period of time is putting too much power in the hands of the auditor, and also just practically speaking, tasking individuals with more than reviewing a specific number of cases might be infeasible in a specific period of time. So our approach is to have dynamic auditing by panels of multiple individuals, and the panels are going to periodically change. And so, the first question is, if you have multiple individuals, multiple auditors in a panel, and the judgments are inconsistent between, the different auditors. So there are disagreements. So how do we handle disagreements? So for that, we have the definition of an alpha gamma fairness violation, which simply means that if there is an alpha gamma violation on a pair of individuals, that means that a gamma fraction of a specific panel perceived an alpha violation on this specific pair. So this is basically a majority-based fairness framework. And this is just the same with a lot of notation, but just report a pair in which there is an alpha gamma violation. And the nice thing about it is that we can vary this gamma parameter to explore the trade-off algorithmically. So like we don't have to ask the auditors different questions. So like the only questions that we ask are about alpha violations. Then the gamma parameter gives us this handle to sort of like aggregate and algorithmically look at the objective that we're trying to optimize. And okay, this is just the same thing in an image.
Can I ask a question? Yeah.
Sure. Yeah. Mm-hmm.
If there is a violation, do you assume that all the judges in the panel would say, yeah, this is a violation, or any fraction would work? I was a little bit confused.
Yeah, sure. So here we have a panel which is parameterized here by alpha and gamma. And so if there is a violation, this is an alpha gamma violation, which means that a gamma fraction, so like you can set gamma between 1/m to 1, and you can have a violation if it's like 1/m, like whenever one auditor thinks that there is a violation, you treat it as a violation. But if it's all the way to unanimous decisions, and you set gamma to be 1, then you only treat violations as cases where the entire panel thinks that there is something wrong about the treatment. Does that answer your question, Saeed?
Yeah. Yes, thanks.
All right. All right, so now that we're equipped with the fairness framework, I'm going to talk about the setting that we're going to explore. All right, so the setting is an online classification setting. Okay, so like in each, it runs in days or in rounds. And on each day, the learner deploys a policy here in blue. And then we assume that K individuals arrive. So this is like the loan applicants, and they receive predictions according to the policy. And then the panel reviews the predictions and the individuals and reports if there is a violation. And at the end of this round, there are two sorts of losses. One of them is the label loss, like the 0-1 loss for the deployed policy on the individuals. And the other part of loss is the unfairness loss, which is if there exists a violation, we penalize by 1. If there is not, we do not penalize. And ideally, the learner learns between the different days and deploys more accurate and more fair policies. This is the same thing, but just formally. And we have these two. So here at the end of the round, we have the misclassification loss and we have the unfairness loss. And the misclassification loss is basically the 0-1 loss extended over the policy. And the unfairness loss is just the existence. So if there is 1 or more violations, we penalize by 1. And it will be helpful in our analysis. We'll also define the Lagrangian loss. So the Lagrangian loss is like a weighted sum of the error and of the difference on a specific set of individuals. So like these two individuals, think about them as the reported violation, this row 1 and row 2, and this will be helpful for us later. And we also define regret for each of our losses, the error regret, the regret. And okay, so how do we measure performance in this setting? So we want to compete, we want to be competitive against the most accurate policy that does not violate individual fairness. So what does it mean? It means that, if this is pi and this is like the most accurate policy in this class, and this Q alpha gamma means that there are no alpha gamma on the specific individuals, on the specific panel in each of these rounds. So like think of each of these rounds with having K different individuals and M different panelists. And this panel can also be adversarially chosen or chosen in any way. So look at all of the policies that do not have alpha gamma violations on each of these days. And we want to be competitive with the most accurate one. And okay, so this is the comparator class. And this is basically saying that there are no violations on these policies. And one important thing to notice is that this class, this Q alpha gamma, is only defined in hindsight, meaning that the realization is both over arriving individuals, over the arriving loan applicants on one hand, but also over panel members. So this is a class that is only defined after the process was done. And we want to have simultaneous guarantees. So we want to have no regret guarantees, which go for accuracy and also for fairness. And one thing that we know is from the Gillen et al. Paper is that if the auditor's judgments are according to a metric form of particular, this Mahalanobis distance parametric assumption, and if the auditor reports all violations, if multiple ones exist, then this is possible. And also, they can get convergence, which is with a logarithmic rate in the fairness regret. And the question that we're asking here is like, if we drop the assumption on the metric form, and also, in our fairness elicitation scheme with multiple auditors, but even with a single auditor, can we still achieve simultaneous guarantees under no parametric or even metric assumptions? And in this line of work, we answered that yes, this is possible. And the way that we achieve these guarantees is that we connect this setting that I just presented to the literature in contextual combinatorial semi-bandits. And I will show now, like in the next slides, that so like under certain conditions, we can use the Lagrangian loss to upper bound both losses. So like both the error and the unfairness loss. And this will be helpful because we will play, no regret versus the Lagrangian loss. So like the plan would be to bound the regret on the Lagrangian loss and then use that to bound each of the two, regret terms simultaneously. And if we have time in the end, we'll see how we construct this Oracle efficient algorithm by adapting the work of Vasilis Irkanis et al., which will allow to have this simultaneous guarantees efficiently. All right, so in the heart of the paper is this reduction. So like, first of all, the contextual combinatorial semi-bandit, I'll just present it in a few words. This is basically a setting where you have a loss vector, in k coordinates, and you have k individuals that arrive, and the learner draws an action. So in the contextual version, according to the hypothesis class, so like each of these vectors of k entries is 0, 1 according to invoking this base predictor, like for each of the base predictors on the k arriving individuals. And at the end of the round, the learner suffers linear loss in these two vectors, like the action vector and the loss vector. And the semi-bandit setting means that the only loss coordinates that are observable for the learner are the ones on which it predicted positive. So like if it was a full bandit, only the inner product would be observable. But since this is called a semi-bandit, this is only the positive ones that get revealed. So the reduction is, there's a lot of notation here, but the only two, so the two main ideas that are important in the reduction is, okay, so first we take the stream of individuals that arrived and the reading of the panel of the violation. And we use this stream and the reading to generate a new stream, which is like a fake stream, which encodes the fairness violation part in terms of the 0, 1 loss. So we see it here in this, this X2 bars is like the X bar, which is like the K individuals, plus we add entries for the reported violation here. And we add fake labels for these entries, like 0 and 1 labels. And this is like the fairness part on the, original stream, but we sort of like inject these individuals again to translate them to 0, 1 loss. And then we feed this new stream to a contextual bandit algorithm, but now we don't have to take care of two sorts of losses, just a 0, 1 loss. And the second part is, this part that you see here is basically handling this one-sided nature of the feedback. So, instead of having, so this is just a 0, 1 loss here. So if you accept someone who's a good candidate or, so this is basically a 0, 1 loss. And we add the vector of ones to the rounds on which, negative or like bad candidates arrive. And this is regret preserving. So, and the benefit to moving to this right-hand side matrix is that when we reject a candidate, the loss is fixed. So like we always have one in the second line. So it's sort of like it makes things easier for us. So it's like a bandit setting now. It's like revealing, the action that we take is like we reveal the loss. And so questions so far? Okay. So, right, so we looked at the reduction and so using this reduction, so what we show in the paper is that, given some algorithm for the contextual combinatorial semi-bandit setting, so like assume that we have some algorithm A, and this algorithm has some expected regret guarantees. So the reduction, we can use the regret guarantees of this algorithm. and basically upper bound the regret for the Lagrangian loss. So what we show is that this construction that we have with these fake individuals in the stream, playing 0-1 loss to the fake stream is really, measuring the Lagrangian loss over the original stream. So, we can inherit the guarantees of the no regret guarantees of this algorithm up to some, this comes from having a longer stream. So like having some inflated stream. So like the dimension is something that extends a bit. And again, found on the Lagrangian regret, but we want simultaneous accuracy and the fairness one. Okay, so one additional step that is helpful in establishing that is that if we look at the Lagrangian regret, we can upper bound this joint term of the unfairness, the sum of unfairness violations times the C times the epsilon of the slack for the fairness violations, plus the regret for the 0-1 loss. So it's like the unfairness regret plus the error regret. And we can, for this weighted sum of them, we can upper bound them with the Lagrangian regret. And this is, you just examine it case by case. But this, this is still not enough. So you could think that, well, I can, if I have this bound and simultaneously upper bound this term and also this term, but we have to be careful here, since if we look at the second term, the error regret, so this part can actually be negative. So what I mean by that is we restrict the comparator class to come from a smaller class of policies that are fair in hindsight. But the algorithm really plays something that is unrestricted. And also the algorithm can shift and not just play the same policy. And so, in terms of error, this term can be negative because that is better than the error of a fixed policy in hindsight. So what can happen? So in general, we don't really care about this regret being negative. This is a good thing. But here, if this part is negative and this is large enough, then what can happen is that the unfairness term, like the number of rounds on which we have a fairness violation, it can explode. It can be linear. So we don't want that. We want the two terms being simultaneously sublinear. And for that, we will need an extra interpolation argument, which is in the papers. But the upshot is that, we can get, so like given any no regret algorithm for combinatorial semi-bandit, we can translate its guarantees to simultaneous no regret guarantees for each of accuracy and fairness, even without parametric assumptions on the metric. And okay, so how am I doing in terms of time? I have time for the algorithm. Okay, so like one thing that is important to note on the reduction part is that the reduction is actually requires that the panel sees the predictions and not the realization. And what I mean by that if you look back at the way that this stream, this fake stream, this X double bar is defined, is by this row T1 and row T2, which is like the individuals on which there is a violation. But to detect this alpha or this alpha gamma violation, the panel has to see the policy and the individuals and the predictions. And where we can run into trouble, so like, if we run the exponential weight style algorithms, we always have the policy explicitly. So we have that, and, we can invoke the reduction. But so for FTPL style algorithms, this is a bit more difficult because they don't explicitly maintain the distribution over base predictors on every round. So like what these algorithms do is that they deploy a policy that is drawn from this distribution and relying on this linear nature. We will see later. But okay, so for exponential weight style algorithms, we can run the reduction, we can get simultaneous guarantees, but the downside is that this is inefficient. So like the time complexity and also the memory complexity is linear in the size of the hypothesis class. And this is the guarantees. We'll go back to this later. So the point that I was making is about FTPL style algorithms. So algorithms that are oracle efficient, so they have access to an offline optimization oracle. And in this case, we have this additional needed assumption for on the hypothesis class of a small separator set. So given these two primitives, we can have an oracle efficient algorithm. But okay, so like where is the problem with our setting specifically with using this algorithm off the shelf? So the problem comes that if we don't really explicitly maintain the deployed distribution that is played on every round, but we sample a single hypothesis from the distribution, the problem is that for the fairness loss, it can be, a gross overestimation, because, if you have, for example, two base predictors who are predicting 0 and 1 and 1 and 0, and the individuals are similar according to a metric. So like if you always sample one of them, you will always have the violations, like a linear number of violations. But if you mix them together and you predict like 0.5 and 0.5 and you send it to the auditor says like there's no problem. So this is basically the dilemma here, which is saying, if we have single realizations, this is not enough in our setting. So we have to actually, estimate this deployed policy, which is not observable to us. And, one potential solution for that, would be to have a closed form expression for the weights. But this is unfortunately for the specific way that FTPL works, this is not efficiently computable. So what we do instead is we resample the deployed hypothesis every round. So we form an estimation of this deployed policy. And so where we can run into trouble with that is that, in adversarial online learning, the realized randomness of the learner, you cannot really reveal it to the adversary. And in our case, the adversary is really emulating the behavior of this panel. And so like in general, the adversary can tailor the losses. So like if it sees the randomness, it can fail you. And, this part of the panel really goes after we establish this estimation, like the estimate of the deployed policy. And so like the nice part is that since the adversary is not, in our case, really adversarial, since this is a panel reporting violations and the panel has to go with the preferences that individuals have in the panel, and we assume that the preferences do not shift according to the way that we estimate the deployed policy, we can actually get away with it. So like we can actually do this and without, having to pay. So this is the idea in the resampling scheme of the FTPL. And all right, so this is the overview of the results that we have. So we have results for the full information setting as well as the one-sided setting. And, starting from T to the 3/4 for the inefficient case for full information, all the way to this guarantee that we have for an efficient algorithm with a one-sided nature. And, K is the number of individuals. So like ideally you would want this to be linear. And you can see that for fairness, the fairness term, we have this 1 over alpha, which we carry over because of alpha being the slack for the violation. We have to linearize over that. And this is the limitations that I just mentioned, that if you have a large hypothesis class, EXP2 might not be the right algorithm. This FTPL style algorithm, but this is in general, not just for the fairness setting that we have here, requires this small separator assumption on the hypothesis class. And we know small separators for conjunctions, disjunctions, parities, decision lists, discretized linear classifiers, but not in general. And due to this resampling, we have this O over T squared calls to the optimization oracle. But ideally, you would want to do better. And a concurrent and just a very beautiful line of research that I did not mention, and I should mention, is the endeavors around rich subgroup fairness, which started with the seminal works of Kearns et al. And Hebert Johnson et al. And many other beautiful follow-up works. And the idea is, in the talk, we really focused on one extreme, like we focused on individual fairness, but rich subgroup fairness is like a nice middle ground between group and individual fairness, where they equalize across a predefined set of this potentially exponentially many groups in the population. And it also allows for significantly stronger guarantees for individuals. So I was writing this slide, I was trying to sort of like compare these two notions in my mind. So it seems like individual fairness sits on one extreme of subgroup fairness. So like you treat each individual as a subgroup, but you don't really equalize across all of the individuals, like just plain simple. But there is this additional primitive, which is the similarity metric, which is giving you this very specific structure on which you operate on. So I think the nice component about individual fairness is that it gives this direct access to auditors or to people's preferences informing the fairness definition. However, it's a trade-off, and it's no. It might be harder to elicit the preferences, and it also could potentially trigger larger tension with accuracy. So this could happen if the similarity preferences are not very well aligned with the labels, and also dependent on how expressive the base class or the predictor class that you're trying to learn. And okay, so the takeaways. So in this talk or in this line of research, we go simultaneously to really like two extremes. Like on one end, we try to give guarantees for individuals, and we try to go to this very strong individual fairness notion. But on the other end, we try to minimize assumptions. So like we try to handle the cases where we have no metric assumption, no parametric form, that data can arrive adversarially, and that feedback is limited. And so we really try to give these guarantees under minimal assumptions. And so we've seen how we have this fairness auditing framework, which can handle multiple auditors and dynamically changing auditors, and they can possibly have conflicting opinions, but we can still utilize this feedback, and we can also algorithmically change the majority parameter to give different points on the frontier. And we've seen that it's possible to give simultaneous no regret for accuracy and individual fairness under these very limited assumptions. Yeah, so to conclude, some future directions, and I think like the biggest future direction that I see is like trying to make these algorithms more practical. So like namely, a few open questions is, so we've seen in this one, we've seen that the rates, dependence on this capital T, like the number of rounds, is not the optimal one. It's not the root T guarantee. And like one question is, can we get simultaneous rates that look more like this T to the 1/2 optimal rate? And also, can we give Oracle efficient algorithms in the general case, maybe requiring, without requiring small separators. And I think one hope is that we use really adversarial learning tools where our model, like the panel is like not really adversarial. So, maybe try to get more juice or like squeeze more juice and utilize some functions that are not currently utilized. And other directions is, if we relax some of the assumptions, we've seen a relaxation of parametric assumptions in the Gillen et al. Paper, but we can definitely go and relax with different forms. So like one interesting case to examine is what happens if panels are not just selected arbitrarily as we have here, but are given from a distribution, like you select jury or like you select auditors from the population. And also another interesting case is like, what if the contexts are adversarial, but the labels are selected from a distribution given the context? So like the time that people apply might be, dependent on the policy, but like the labels are like pretty much the credit worthiness of these individuals that apply. And, finally, getting faster algorithms. So we've seen this, that we have to invoke this Oracle like a quadratically number of times we would want to improve over that. That's it. Thank you.
Thank you, Yahav.
Yeah, we have another 10 minutes.
Yes, do we have any questions for Yahav? Feel free to unmute yourself and ask questions.
Try it.
I was going to ask you about the reduction that you had, like to get that Lagrangian loss, which made a fake stream.
Right.
In that fake stream, you had these row 1 and row 2, which were the individuals that the judges found that they're treated unfairly. I was going to ask, like, if, like, for example, 60% of the judges say these are the individuals that are treated unfairly, and like other 40% says, like, find another pair. Will you, like, which one are you going to choose? Like, do you take the set, or do you have to choose only one out of all the found unfairness violations?
Yeah, so in our formulation, we are happy with, with having one. So like, if the requirement is alpha violations on, like, say, 60%, like as soon as we have one pair on which there's a disagree, on which 60% agrees that there is a violation, you could report any one of these pairs.
So, and is that how this conflict of opinions don't matter? Because you can have multiple found fairness violations, but only one of them can be chosen, and that's fine.
Oh, I think
where does the conflict of opinion?
Yeah, I was thinking more about the conflict of opinion as, auditors having different preferences in the panel. So, some think that these two individuals are more similar, some think that they are more far away. And so, they might not agree on how the treatments are, like, if they're unfair or not. And so by requiring the majority, we kind of like, we say that, what is the required level of agreement for us to, to issue a violation or to treat this as a violation, as a case that we have to penalize against.
And is there any follow-up work on this domain of having a panel of auditors instead of a metric?
I think there's one work that Aaron, Chris, and I think Logan and Michael, I think they have something in the batch setting, but the setting is quite different. So like the way that they handle the violations, but I think that over there they have a group of auditors, which is like a fixed group of auditors. But other than that, I don't think I've seen others. Yeah.
Okay, thanks for the talk. I'm gonna stop.
All right.